Okay, Bismillahirrahmanirrahim. Assalamualaikum and a very good day to everyone. So today we will continue to our new topics in electrostatic field, which is regarding on the electric flux density. Yeah. Okay, here is the learning overview that what we're gonna go through in this topic. Okay, first of all, you're gonna be introduced with what is electric flux is, yeah, and then you also will get to know what is about what is the electric flux density. Okay, the symbol, the formula, and the definitions. And also we can try to look about the applications of the Gauss law, where previously I believe we have used Coulomb's law in order to determine or to calculate the electric field intensity. But in this slide we will introduce to you guys how to calculate the electric field intensity by using the Gauss law. All right, so the keywords that we're gonna be seen in these topics, okay, is regarding on the electric flux. Please cancel this Faraday. Okay, it is not included yet. Electric flux density and also the Gauss law. Right now, let's look what is electric flux. Yeah, so electric flux or the symbol is given as psi e. Okay, so this symbol, yeah, so this symbol is called as psi e. All right, it is known as psi e, and the e down here is referring to the electric field. Okay, electric field. So this is known as psi, and e here is represent the electric field. Okay, so what is electric flux? Electric flux is an imaginary line. Okay, it is a line that we know it is exist, but we can't see with our naked eyes. Okay, it is an imaginary line, and it is usually pointed outwards from the electric source. So there are 4 electric sources. So please recall back what are the electric sources. So the electric flux will usually, yeah, it's like a line that is coming out or pointed out from the electric source. Okay, so electric flux also yeah, is a number of lines coming from the electric source, and it is in a scalar form, meaning that the direction is not considered. Okay, there is no direction. Okay, however, we know the line is pointed out, but it is the direction is not considered. All right, and the direction usually is the same as electric field. So electric flux is, okay, electric flux, yeah, the psi e is equals to q, how much charge that is contained inside the electric source. Okay, so electric source, we know electric source charges, yeah, is know the units is given as coulomb. So since that it is equals to electric flux or psi e, so therefore our psi e also will have the same unit as our charge. Okay, so psi e is equals to q. Okay, remember psi e is equals to q if it is a pointed electric source, point electric source, so therefore q is equals to q, right? But if it is a line electric source, your q will gonna equals to rho l dl, right? And if it is a surface, it's going to be rho s ds, and if it is a volume, it's going to be rho v dv. Right? So in this case, if you look at the figure here, okay, the figure that is represented in this slide here, there are three lines that is pointed outwards. So what can we say? Okay, we know electric flux is equals to q, so therefore the q is equals to 3, yeah? Is equals to q, and the number of this line is equals to the number of electric flux, so it's going to be 3 coulombs. All right, okay, let's look to our first example here. Okay, that has been provided to you. The question asks to find the total flux 1 meter from a 12 nanocoulomb point charge located at the origin. So first of all, we need to extract what are the information that is provided inside this question, right? So let's extract the information. So we know the source of the electric source is a what? Is a point charge. Okay, so what is the value of the Q? So the value of the Q is 12 nanocoulomb. And where does it located at? It is located at the origin, meaning that 0, 0, 0. And what we need to find? We need to find the total flux. So total flux, it is psi E, right? Where? At 1 meter. Okay, so if we can illustrate it, or if we can draw the diagram based on the informations from the questions that we have here. Okay, so the diagram is going to look as such, right? Okay, so this is going to be the x-axis, y-axis, and z-axis, right? So this is going to be our electric source. Okay, so we need to find the total flux 1 meter away. So this is our imaginary lines, which is actually 1 meter away from this origin. Yeah, okay, 1 meter away, 1 meter away, 1 meter away from it. Okay, so we know that the total flux is equals to the total charge inside the imaginary line. So psi E is equals to Q. Okay, we know this formula. So what is the value of Q now? The value of Q is 12 nanocoulomb. So therefore, the answer is 12 nanocoulomb. Alright, so now I would like to twist this question. How if they ask you, find the total flux at, use this different pen, yeah, color, at 2 meter. At 2 meter now. So of course, the imaginary line we're going to look much more larger, yeah. Okay, the imaginary line now is become larger because it is 2 meter away. So how much is the total flux? Will the total flux increase? Well, what will going to happen with the total flux? We know the total flux is equals to Q, and we know the Q is coming from the electric source. Yeah, electric source, which is now our electric source is this point charge. So what we're going to do? It will remain as 12 nanocoulomb, or you have to multiply it with 2 since that it is a 2 meter. It will remain. The answer is it will remain as 12 nanocoulomb because although the distance is become farther, maksudnya the distance is become bigger, although the distance is bigger, however the source, okay, the energy, okay, that is contained inside this electric source is only, the charge is only 12 nanocoulomb. It will not double, it will not become lesser. Alright, it will remain the same. Okay, alright, so please remember that. Yeah. Alright, now let's look into example number 2. Find the total flux on a surface of a sphere. Okay, the sphere has a uniform surface charge density also. Okay, this is the first information that we have, yeah, from the question. It has the surface charge density of 24 nanocoulomb per meter squared, and the charge is 0 everywhere else. It is 0 everywhere else, and the radius of the sphere is 10 meter. Okay, so surface charge density, meaning that the value of the rho s is equals to 24 nanocoulomb per meter squared, and it is rho s, it is on the surface, so meaning that the charge only exists at this surface only. I'm trying to use a different color of this laser. I think it's possible. No, yeah, it's not possible. Right, the charge is only exists at this surface, meaning that inside the sphere there will gonna be no charge at all. Outside the sphere, of course lah, yeah. Inside the sphere there gonna be no charge. Outside the sphere we're gonna be no charge. The charge only exists on the surface only. Alright, okay. So the surface of sphere, so the radius is given as 10 meter, yeah. And what we need to find? We need to find the we need to find the, I will try to change color. Okay, we need to find the total flux, which is E. Okay, so we know E is equals to what? E is equals to Q, and Q for surface is what? Rho s ds. So we need to find our ds now. Okay, total flux is equals to total charge enclosed. So that, okay, since therefore, yeah, we know psi E is equals to Q enclosed, and Q enclosed is equals to the integrations of rho S ds, okay, rho S ds, the whole surface, yeah. So ds we know for the sphere we have on r direction, theta direction, and phi direction. So which direction should we choose? You have to look back to your diagram. So we have a sphere now. So for as I mentioned earlier, we have to take a sample. Let's say this is our sample, and the direction usually we take 90 degrees normal to this sample. Okay, 90 degrees normal to this sample. So 90 degrees normal to this sample for this sphere, it's gonna be in r direction, yeah. So it's gonna be r direction. So in r direction, they're gonna be r d phi multiply with r sine theta. R d theta, yeah. R d theta, r sine theta d phi. Okay, so therefore your ds is gonna be r squared sine theta d theta d phi. So you just rearrange here to make the mathematical look nicer. Okay, so we know already our rho s. Okay, we know the limit of phi and the limits for pi. The limit for phi and the limit for theta. Right, so you just have to substitute inside the equation and you will get your answer, which is the total flux at 10 radius of the sphere will gonna be 9.6 microcoulomb, right? Okay, now let's look the last example. Okay, for the electric flux. Oh, I have another example. Sorry, not last example. Yeah, example number 3 for the same question, using the same question just now. Okay, so same structure, same sphere as in example number 2, but now we want to find the total flux. Okay, just cancel one total, one there here, yeah. Find the total flux at r is equals to 5 meter from the center of the sphere. Okay, so now this is the questions just now. Okay, where it's given that the rho s is given as 24, yeah, no coulomb per meter squared. Okay, and the sphere has a 10 meter in radius, yeah. And now, okay, the question asks about to find the flux at r is equals to 5 meters from the center of the sphere. So meaning that this is our imaginary lines where it is 5 meter inside, yeah, 5 meter inside. So our imaginary line contain inside the sphere. All right, so we know that the total flux is equals to the total charge enclosed. So charge enclosed, okay, psi E is equals to Q. All right, so inside the sphere, I think I did make clarification just now. Inside the sphere, there is no charge. Charge only exists at the at the surface only. So inside that, the value of the charge is equals to 0. Okay, is equals to 0. So therefore, the total flux or the total charge enclosed at 5 meter is equals to 0. Okay. Okay, now we want to do the same questions, but now when the radius is 5 meter from the surface of the sphere. Okay, so this is the structure. Okay, so this is the structure. It is 5 meter from the surface of the radius. Of the sphere. So meaning that you have to add another 5 meter. Okay, you have to add another 5 meter from the surface. So now the total radius now is 15, yeah, 15 meter. Okay, so what is equal the value of the Q enclosed? So this is our imaginary line. Okay, so our imaginary line now, inside the imaginary line, will there any charge have inside that? Yes, right? We have the charge inside here, right? So what we need to do? You need to we need to use the rho s ds, but now your r is where? Your r is only 10, although the total r is 15. but R that has the charge is only at 10 only. Okay, only the radius at 10 that the charge is exists. More than that or lesser than that, the charge will not exist. Yes, the charge will not exist. So your R now is equals to 10, and your answer should be as same as the previous questions. Okay, the earlier questions that we do just now. Example number 2. Okay, so I hope you're very clear with this. Yeah. Alright, now let's look at example number 4, where in this example, they give to you, okay, infinite line charge of 10 nanocoulomb, which is located along x-axis, okay, and we need to find the total flux on a 2-meter cylinder of radius A, and the axis of the cylinder is parallel to x-axis. So we need to find what are the information that we can get from these questions here. So we know it is an infinite line charge, so meaning that it is going to be rho L, and the value of the rho L is equals to 10 nanocoulomb per meter, and it is located along x-axis. Okay, and we need to find the total flux, which is psi E. Okay, and the shape of the total flux is going to be in the cylinder shape, where it's given the height is 2 meter and the radius is A. Yeah, and the cylinder is parallel as well with the infinite line charge, which is to x-axis. Alright, so if we can draw or if we can illustrate, so we have an infinite line charge along x-axis. So this is positive infinity, and this is going to be negative infinity, and the value of the rho L is given as 10 nano. Okay, and then we need to find the total flux, where the total flux must be in a shape of 2-meter cylinder with a radius A. Yeah, 2-meter cylinder with a radius A. So we know, okay, the radius A, it's going to be 2 meter. Alright, so the total flux we know is equals to, okay, psi E is equals to Q enclosed. Alright, and our Q enclosed we're going to be rho L dl. So we know this. Okay, and rho L dl here will depend on what type of the electric source, right? So in this case, our electric source we're going to be this is our electric source, right? So the appropriate orthogonal coordinate system that can suit with this electric source, we know already must be a cylinder. So cylinder, the dl will going to be r on dr, dr, yeah, dr on r direction. Okay, dr on r direction plus r d phi on phi direction plus dz, yeah, plus dz. So dz we're going to be the height of the cylinder, of the total line charge, right? Of the line charge, right? But in our cases, the height is located, since that it is located or it is lies along x-axis, so they're gonna, instead of dz, it's gonna be dx, right? Okay, so let's see all of this variable. There are gonna be no changes on r, right? So of course this is gonna be 0. There's also no changes in phi direction, so of course this is going to be 0. But of course there going to be the changes in dx, because it depends on how long of our source, yeah, of our electric source here. So only dx left behind. So our dl will going to be dx, right? So if we do the integration, okay, rho L dx, and the limit will going to be the height of where the electric charge is contained. Okay, so it contains only inside this cylinder. Okay, only inside this area that we want, yeah, our area of interest. So it's going to be from 0 to 2 meter. Okay, from 0 to 2 meters. So we will get the answer. We're going to be 20 nanocoulomb, right? Okay, now let's try some practice. So we have practice 1 here. So in this practice, they said uniform line charge with rho L, which is equal as 3 coulomb per meter, lies along x-axis, and we need to determine the electric flux, meaning that our psi E crosses a spherical surface. So our electric flux now is a sphere surface. Okay, it is a spherical surface centered at the origin with the radius is equals to 3 meter. Okay, so if we can illustrate the structure, so the structure will gonna be, we have an infinite line. Okay, we don't know where it is starting at and until where the line is extend to. Okay, so we know that it is an infinite line that is along x-axis. Okay, so this is along x-axis, yeah. And then we need to determine the, so this is our y, this is our z. Oh, I should use different color of the pencil. Okay, but then it's okay, let's use different color for the line charge. Okay, so this is the line charge, alright. So this is on x, this is on z, and this is gonna be on y axis, alright. So the structure of the electric flux, so electric flux is crosses a sphere surface. So now if we can draw a spherical surface, so this is gonna be the spherical surface that is centered at the origin. Okay, and the radius of the surface is given as 3 meter. Okay, so the radius is given as, how to draw the radius? Okay, the radius is given as 3 meter. Okay, so now we know the electric flux will gonna be the flux that is amount the total of charge that is have inside this sphere. So to know that, so our psi E will equals to Q, right? And the Q will gonna be rho L, since that the source given to us is rho L, and it must be dl, right? So the dl now same as previously. So the dl is a line, so we have to use cylinder, and since that the line is lies on x-axis, so it will gonna be rho L dx. Yeah, it is along x-axis, so it's gonna be rho L dx. Okay, so now what is the limit for this structure inside the flux, yeah, inside this sphere? So what are the limits that we should do, or we should take here? Rho L dx. So the limits were gonna be from -3 to 3. Why from -3 to 3? Because we know the structure is a sphere. It is spherical, so it is have -3 in front here, and also +3 in front here, and -3 at the back there. So the limit we're gonna start from -3 to 3. It is not from 0 to 3. Okay, and when you calculate, you should get your answer will gonna be 18 millicoulomb. Alright, so I hope this is very clear to you. Okay, let's look the last questions that I have provided inside your slides regarding the electric flux, which is this practice 2. Okay, so the question said a 25 millicoulomb, yeah, point charge is located at the origin, and we need to calculate the electric flux that is passing through. Okay, the portion of the first the portion of a sphere where r is equals to 20 centi, bounded by theta is equals to 0, okay, to pi, and phi is from 0 and pi over 2. Okay, so now we need to draw, or we need to illustrate, yeah? So we have a point charge here. Okay, so it is, the Q value is 25 milli. Alright, it is located at the origin, and we need to find the E, and the structure of the E will gonna be a portion of a sphere. It is not a full sphere, it is only a portion of a sphere, where r is equals to, given as 20 centi, and the theta is given at from 0 and pi, and phi is 0 and pi over 2. So if you can draw the axis for A, so this is our x, this is gonna be our z, and this will gonna be our y axis, and we have a point charge here. Okay, so this is our point charge. Okay, alright, so this is all a point charge. Alright, so the total Q of this point charge is given as 25 milli. Okay, and we need to find the electric flux from a portion of the sphere, or if we can draw the portion of the sphere. So the sphere is from it is, the R is equals to 20. Okay, the R is equals to 20, meaning that so this is 20 centi. Remember, it is a centi, yeah? So it's gonna be 0.02, yeah? So this is gonna be the R, 0.02, and then the theta is from 0, so theta is 0 is at here. Okay, so this is the 0 theta. So okay, let's draw it. I try to draw it properly. Okay, so theta here 0, and then and pi. Okay, so 0 to pi is here. Okay, here is 0 to pi, and the phi is 0 and pi over 2. So 0 is here, 0 is located here, pi over 2 is located at here. Yeah. Okay. Okay. Alright. Sorry, my drawing is very bad here. Okay, so let's assume that the radius is 0.02. Okay, so if you can see here, this is not a full sphere. Yeah, this is only a half, sorry, a portion, yeah, a quarter, 1/4 from a full sphere. Okay, so we know already the formula. Psi E is equals to Q, since Q is a point charge, so Q will be Q as it is, where our Q will gonna be 25 milli. However, the total Q will not be this inside this sphere. The total Q is not equal to 25 milli because not all the point charge will be inside this sphere. Yeah? Only 1/4 of the point charge will be inside. Okay, will be inside this sphere. Will be inside this sphere. Okay. Only 1/4 of the total flux that will be inside this sphere. So therefore, your answer will gonna be 1/4 multiplied with 25 millicoulomb. Alright, for question A. Alright, so now let's try for question B now. For question B, the closed surface of R 0.8 meter and Z positive negative 0.5 meter. So we can see the variables here is given as R and Z. So what are the appropriate orthogonal coordinate system? It must be a cylinder, because cylinder the variable is R, phi and Z. Okay, we have the information of R, we have the information of Z, but then information for phi, we can guess that it is a full cylinder actually, right? So if we can draw the structure, it's gonna be X and Y and Z here. Okay, so there is a point charge that is located here, 25 milli, and then we can draw the structure of the cylinder. Okay, where the structure of the cylinder is the R is given as 0.8. So 0.8 is given here. It has the height of 0 positive 0.5. So this is positive 0.5. Down here is negative 0.5. Sorry. Okay. Alright. So we assume that it is a total cylinder, yeah, meaning that the whole cylinder here. So what are the value of the psi E now? is equals to Q enclosed. So inside this cylinder is contained this whole point charge, right? Meaning that the flux from this whole point charge is possible to be distributed along this cylinder. So therefore psi E is equals to Q enclosed is equals to 25 millicoulomb. Alright. Okay, I hope this is very clear with you guys. Okay, with your understandings of flux. So what is flux? Electric flux actually, if you can summarize, flux leaving the surface here, yeah, is equal to the charge that is enclose the surface. Okay, so this is the meaning of the flux, electric flux actually. Flux that is leaving the surface is equals to the charge that is enclosed inside that particular surface. Alright, so thank you very much. I hope you are very clear with this topic.